In this video, we'll discuss stochastic gradient descent with momentum. We saw momentum before in the context of tackling ill-conditioned problems better, and now we'll combine it with SGD in the straightforward way to yield SGD with momentum. And SGD with momentum is actually already the best available optimizer for some problems in deep learning. Let's dive right in. Stochastic gradient descent with momentum. So momentum is one of the core techniques in order to speed up SGD, and it's important to understand how it works. We've seen momentum before in the context of ill conditioning, and I've also seen that for the quadratic function, which is over here, we can actually improve convergence rates by using momentum. The main idea here is to make the updates smoother by keeping a history. So not be misled by these gradient directions that standard SGD would have, but actually smooth out over the history in order to get an overall gradient direction that's more pointing, well, towards the goal and makes much more progress in each step to converge faster. The update step more formally can be written like this, where you have a velocity v, and that is updated by dampening the previous velocity and then subtracting the current gradient, approximate gradient, times the learning rate. And then that velocity is simply added to your current parameter vector in order to update that. Visually, we've seen this described as such before with slightly different notation. So the velocity, previous velocity, is basically the difference between the previous theta and our current one. So this vector here is v. And the extrapolation step that we saw before, that is precisely the dampened velocity. So this beta v here. And the step we make is just our standard gradient update step plus the dampened velocity. So this gradient step here plus this here leading to this update equation, and this is equivalent to this update equation here. Here it's written as a gradient of v, here it's written as g hat, but this plot here is from standard momentum in gradient descent, and here we're in SGD. That's where we have the approximate gradient g hat. But that's really the only difference between these two algorithms. And so this velocity v here can be seen as an exponentially decaying moving average of our past gradients. And we saw before that this update can also be written like this, where you have, where it looks a lot more clear that this is an exponentially decaying moving average of the past gradient. So we have all our past gradients here. Our current gradient is g hat sub k. So we decay our current gradient by, nothing at all, beta to the power of 0. So we use our current gradient. But past gradients, for example, from 100 time steps ago, get dampened by a multiplicative factor of beta 100 times. So there's not much left from them. And that is a good idea, especially in stochastic gradient descent that moves around the space quite quickly. We actually don't want to remember the landscape that we saw 100 steps ago too much because, the landscapes change, and so we also want to adapt to that. And so we want to be able to partially forget some of the past in order to keep updating quickly with respect to the current features of our landscape. So momentum has some pros and cons, and we can visualize that again with this little visualization here where we have a single parameter vector, a parameter theta, and here we have f of theta. And in this case here we have a small learning rate and vanilla gradient descent, well, converges very slowly. Now in this case, all of the gradients point in the same direction, and so momentum would actually learn to accumulate these gradients, each of them with a exponentially weighted, so forgetting the past gradients, with an beta to the power of the distance of the gradient. But nevertheless, we would learn to actually speed up. So gradient descent with momentum would learn to make larger steps because, well, all of them point to the same direction. And so this lets us accelerate learning at flat spots where, well, all the gradients are pointing to the same direction, but the gradients are slow, then they accumulate over time. We saw before that it can smooth zigzagging, but now we'll actually also see that it can cause additional zigzagging. So if you have gradient descent with too strong a momentum, then we can actually, well, we accumulate this initial step here and this. You see that the errors are getting larger, the updates are getting larger. Then here you're already at the optimum pretty much, but you keep going because of your momentum, and it takes quite a while until you actually reverse. And well, let's say this is actually a little bit lower than here, then this process will converge, but it will zigzag very substantially. So too strong momentum can also cause additional zigzagging. Now, one additional benefit of momentum is that it can actually slow down when the signs of our partial derivatives change. So we've seen this case here before, where vanilla gradient descent would actually diverge because it's overshooting, because our learning rate is too large. But in this case, all these gradients are actually pointing in opposite directions. So what gradient descent with momentum would do with that is, well, starting at this initial point here, moving here, then moving there, because the momentum is holding it back from going all the way here. And so then you would already be here and basically then move on a little bit further and basically converge. So you can actually get rid of this problem that you have gradients pointing in opposite directions. If that is the case, then momentum makes the optimization slow down. So you accelerate in flat spots, you slow down in spots where it's unclear which direction you should be going. And that's precisely what you would want. Now, one additional disadvantage of momentum is, of course, that there is this additional parameter beta. This definitely wants to be tuned. And well, this parameter beta actually lets us subsume SGD without momentum. So if we were to set this beta here to 0, then we would just completely forget our previous velocity, and all we would just do is standard stochastic gradient descent. So it is a strict generalization, and therefore it typically helps if we tune this hyperparameter beta properly. All right, this brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.